Brilliant. So, hi everybody, thank you for joining. Welcome to this Safe Landing Airside chat. You might have heard about fireside chats with CEOs, so we've added our aviation spin to that and called them Airside chats. My name's Finley. I'm Finley Asher. I'm an aerospace engineer and I'm the think tank lead at Safe Landing. We're a global community of aviation workers, students, and enthusiasts who care both about the future of our industry and also the future of our planet. We're keen to use the unique perspectives that we have as those actually working within the industry and operating it, to help steer our industry towards more sustainable skies, and a future of clean flight that can help preserve the beauty of flying for generations to come. So we want to improve our knowledge of, and help kind of promote potential methods of low carbon and zero carbon air travel. We're really keen to hear from industry experts and innovators that are really pushing the boundaries of that transition. So yeah, that's the purpose of these Airside chats. So yeah, today I'm really delighted. We've got Kenzo and Tomas here of NOEMI Aerospace. Welcome to you both. Thanks for being here. Do you want to both give yourself a quick introduction?
Yeah, sure. Hi, everybody. My name is Tomas Brødreskift. I'm a CTO and co-founder of NOEMI. And I have about 16 years of being involved with developing electric, specifically a small two-seat electric seaplane and electric aircraft in general. My background is within product design mainly, but I've been flying since I was very young. So I'm very, very happy to be involved with this project now, and joining me is Kenzo, my colleague here. So,
hello everyone, my name is Kenzo. I'm responsible for the flight physics team. I've been working in aerospace for about 10 years, and I've been here in NOEMI Aerospace for the past 2 years, and I'm really excited about this project, and I also appreciate the invitation from Finlay and his group. So excited about this talk.
Yeah, thanks.
Thanks, guys. So they have some slides here that they're going to use to talk through a bit about the company and their journey so far. So yeah, before we get into the company and the aircraft, could you both start by talking us through the journeys you've been on before you joined NOEMI? So like what motivated you to get into the world of aviation and the world of sustainability?
Yeah, I can start a little bit on the journey. I mean, I go way back in terms of interest, I would say. You can see some of the aircraft that shaped my journey on this slide. The middle one there, the long EZ, which is a very unique design. That was a home built that my dad built the year I was born, actually. So I kind of grew up in that home build community and got very interested in the field at a very young age. Started flying gliders. So the other picture there, the glider, started flying that at 15, and then got really involved with flying as a hobby, mostly. And I was always like drawn between whether or not I should become a pilot or not. And there was a lot of coincidences, of course, as there always is in life, but ended up choosing to study industrial design. So I did a master's degree in industrial design. During those studies, I met an aircraft designer, an older guy in Germany, who I was very inspired by. And that kind of pivoted me towards this P2 aircraft that you see down there, the aircraft with the propulsion unit on the tail. That was sort of a replica of some of the designs he made, Günther Perschel, down in Germany. And I started a small company in 2010. I think we established that approximately. And something that I thought was going to take 3 years went into 7 years of development. So hybrid systems, electric systems, getting into all the nitty-gritty details of aircraft design, and gathered a group of people around that project. And that led us into sort of where we are today, where I met Eric Eaton, the CEO of NOEMI, in 2021. And we then started talking about what would it look like to do this at a bigger scale, a commercial scale, which was also sort of my goal as well when I started out, that I wanted to, at some stage, make airplanes that would actually have a societal impact, which means you have to go into transport sector type airplanes. So we did a small pivot where we did an electric race plane as well. So there's a second race plane or a second electric aircraft that was in the portfolio, so to speak, project. And then in 22, we could launch this project, and as we've sort of been slowly growing since then, and I'll get back into a little bit more detail on that after this.
Thanks. So, Kenzo, what about you?
Sure. So, yeah, I started working with aviation back in 2013, I think. So there was this master's program that the Embraer sponsored, and that was very, very nice. That you kind of got involved in the industry, but there was also a lot of theory and these things. And that's I didn't know so much about aviation at the time. I think I didn't even know what an elevator was. But I quickly fell in love with the subject, and I've been working with it ever since. So I was lucky enough to work on the E2 program. So I've worked on that program for, as I said, about 6-7 years, and I had the chance to work in the 3 aircraft. So from the smallest to the biggest one. When I started my career, I worked on the E175. That was quite a nice project to work with because it was more or less in the end of the preliminary design. So there is still a lot of discussions and still lots of very interesting things from a flight physics perspective. We got to do a wind tunnel of it, got the chance to spend like 2 months in Netherlands testing it, so that was pretty cool. And then more towards the end of my career, I worked in the 190 and 195. It was also a very nice project. We were developing the auto landing system for those 2 planes, and it was very challenging for a wide variety of reasons. There were also things like the pandemic happening, so we were flight testing this plane all around the country during the pandemic, so it was very challenging. I forgot to mention, but I studied in ITA in Brazil, so that's an aeronautical institute. And from there, I moved to KTH, as I mentioned. I took part of my PhD there. It was related to the Gripen project. So Brazil had just bought a large number of Gripens, and as part of the offset that was put together between Sweden and Brazil, there was an academic side, and through this academic side, professors from KTH started visiting ITA, and then I got to know them and ended up moving to Sweden, what was supposed to be something temporary, but later on became permanent. So I then moved there as a postdoc researcher, was there for 1 year. But as I mentioned, I didn't really like academia so much. Some people find it funny when I say this, but I have a feeling that startups, they have something that they're somewhere in between industry and academia, because you get the chance to do a lot of stuff from scratch. You get to do a lot of things that require, let's say, a lot of theory somehow, right? Because you need to put together models and methods that usually when you work in a well-established industry, all of these things are quite well set up. In a startup, you basically need to do that yourself. So I think it's a good compromise between academia and a big industry in that sense. So from there, I moved to Heart Aerospace. So that was my first startup. It was in Gothenburg in Sweden. And I was there again as a flight physics engineer. I was very specialized in flight dynamics. So we were basically putting together the airplane model. We did a very small wind tunnel. And put together the simulator and that sort of stuff. So I was there for about 2 years, and from there I moved here to Norway. I really like the project that Thomas is going to talk a little bit more later. But I thought it made a lot of sense from a business case perspective, and it seemed, having come from Heart, I understood the challenges related to batteries, and I understood that range. For electric planes, this is perhaps one of the main challenges, right? To get a viable product within today's technology. What I saw in NOEMI was the possibility to have a business case within a short range, within a small range, and to therefore have some sort of sustainability impact by doing so. So that's how I basically ended up liking the project very much and decided to move here. And I've been here for the past 2 years, trying to put together the work for flight physics.
Great. Well, that's a really good segue into then telling us a bit about uh, NOEMI. What is the mission of your company and your plans? Be good to hear a bit more about
Yeah,
that.
sure. And look a little bit at the sort of the phases we've been through already. So it started out in 2021 with this very small group, I'd say. Let's say 3 to 5 people, I would say we were at the time. That started out as a feasibility study, more or less, like looking into, is this at all a possibility to do? Kenzo mentioned weight of batteries, so it was really trying to pinpoint what the weight of the aircraft needs to be to carry enough energy to be able to do the business cases we want to do. So we started out smaller. So the first aircraft here, the first concept was only, I think, 4.5 tons or something like that. And after that feasibility study, we sort of went further. We scaled it up quite a bit. So we went to 5.670 kilos at the end. At the same time, we're doing a seaplane, so it requires a lot of insight into the hydrodynamics of the airplane as well. So we're doing a sort of a boat as well as an aircraft. So I sometimes say it's almost 3 times as much stuff to look at because you have all these aspects that you need to deal with. So we did a lot of that, kind of started out that way in the beginning. I would say at that time was quite rough, because we're sort of very hands-on with building models and scale models and putting them in the ocean and trying things. But it wasn't until Kenzo came on board that we kind of really started to put this into sort of I'd say a data gathering method that made sense in a way, like a scientific sense, right? Because back then we were doing a lot of, I would say, trial and error based methodology. And Kenzo brought more of this science to the mix and kind of tightened up everything. So in 2023, we had sort of a first version of the airplane, but we continued to change the concept between 23 and 24. We changed some battery configurations as well. The batteries went to the back of the fuselage instead of down in the hull. So we did some major changes to the config. Ended up doing like a second concept freeze before 24, and then we really went full on, and Kenzo's going to come back to that, full on scoping out the final version of the airplane from 24, which we basically froze at the end of last year, with still some small details being worked on, but it's been quite an interesting journey so far.
And just to ask some, this is just really basic questions for people that maybe aren't that sure. Is it fully battery electric powered, so that the only power source is batteries? And can it only take off and land from the water? Is that the...
Yeah, so it's a fully electric aircraft concept, and it's an amphibious airplane. So this works from airport to airport, airport to port, water to land, anything in between. That's the baseline. Now, of course, we have an aircraft airframe that can accommodate also other technologies, right? So we're thinking of an airplane that can be hybrid versioned later on, or even go as far as doing a conventional layout as well. Mm-hmm. We want the airframe to be sort of a flexible baseline. So we're doing analysis on the side, but the aim has always been and will always be to go to the market with a pure electric version of this, because the business case is there and it's available to us. And to segue into that, this route between Bergen and Stavanger, I would say, is the inspiration that started the project in a way, because the CEO is from Bergen and Stavanger is the 3rd or 4th largest city in Norway. And there are about 500,000 people that travel this distance on aircraft. So basically 737s and Dash 8s every year. And it's only 157 kilometers. So that's a classic route that would save you a huge amount of time if you could go city center to city center rather than airport to airport. Mm-hmm. and there are no other transport modes that really do much for you. I mean, it's a long time to go on any other mode, and that's a classic route that I think fits extremely well to that seaplane case. And if you're sort of doing that already there are thousands of routes of this kind, both in Norway and around the globe. So since then we've already sold a lot of airplanes across different regions in the world that have similar challenges. So islands, mountains, fjords, etc. That's what you're sort of looking at, right?
Yeah, just looking at the coastline, you can see why it takes so long in a
Yeah.
bus, car, and ferry to get around all of the different tributaries and mountains that you can't see as well. So yeah, just in terms of your design, then, whereabouts are you at, and what's the maturity of that like? And I guess, are you developing like side by side tools to do this as well? Sorry, if you wanted to cover some other stuff first, actually, I can let you go back.
No, I think that's okay. I think it's better if we just did like that.
No worries.
Yeah, so in terms of we have just finished what is called a PDR, which is a preliminary design review. So the process that we sketched in here is let's say a classical project, a classic sketch that you find in airplane design books, right? So we start with the requirements and the concepts, and then based on the technology that you're looking into, you start what people sometimes call a gas sizing. And then from there, you start a more quantitative sizing, you iterate between the different technologies. And then you start adding more and more technologies like structures, landing gears, systems, and then you end up with the concept that we are at the moment. So this is more or less what Thomas explained, right? Back in 2022, we were somewhere like this. We already knew that we were going to be conventional. We already had a set of requirements for the propulsion. But then as we onboarded more technologies and as we started looking into more details about the batteries and these things, we evolved to the current basically outer mode line that we have now. And I mean, we started in the very beginning with basically just some empirical methods, and then we evolved to CFD. So we have recently done quite a lot of CFD studies, numerical studies of several different configurations, several different regions, and targeting different aspects. We've also studied a little bit on the water, and then we moved to the wind tunnel and also did some scale testing in the water. And now all of these things are basically culminating on a flight simulator that we have the pilot testing all the time, quite often. So that's more or less the level of maturity that we're in. We moved from more statistical to quantitative, going from some empirical to numerics, and finally testing and having the pilot in the loop at the moment. Yeah, so that's the aircraft. I'm not sure if we had shown any rendering of it, but it's basically 100% electric. We're targeting about 1 hour endurance plus reserves, and it should carry about one ton of payload, and it should be
Talking about this being the first fully electric seaplane in the world. I know there's some others developing it, but none that are certified yet. So what sort of innovations are in here? What makes it different from other aircraft that exist today? And I suppose, how does like the fact that it's electric propulsion enable some of that as well?
We can go to the slide with the twin otter.
Yeah. Let's start with this one.
Just that one, yeah. Because I can just mention that for the most part, the conventional seaplanes, the thing we think about when we think about seaplanes are float planes. Essentially, land planes like the twin otter, the Cessnas, Cessna Caravan, Cessna 206s that have been modified with floating devices to go in the water. So when we talk about seaplanes, usually people think about these because that is the 600 plus commercial seaplanes in the world that operate. Most of them, I think almost all of them, are like this. Many of the operators would ask us, the first question they ask us is, why don't you just electrify this guy? You know, because they love these airplanes. They've been operating them for the last 50 years. It's easy to understand that they would like to proceed that way. We have to explain that what we need to do is to be way more efficient. We need to get much less drag off our airplanes. So you can see the frontal areas on these two airplanes that you can expect to see quite an improvement on a flying boat. Now, the benefit of the float plane is, I would say, has a lot to do with what's happening in the harbor area. When you're taxiing around on the water, you're high off the water, you have a good overview. You also have sort of your docking infrastructure with you, so you can step onto the float and actually maneuver and grab a dock and stuff like that. Those issues we have to solve on the infrastructure side, because to be efficient, we need to be lower in the water. We need to land on the hull itself, and we need to make some infrastructure to fit the airplane. So that means there needs to be a dock associated with the airplane and things like that. There's things we work on in parallel. But we have to go that way. Otherwise, there is no way we can get the range data that we want out of our airplane. So that might be a good reference for people to understand why we have the config we have.
Yeah. Maybe just to complement that, in terms of innovations, given that it is a seaplane, there were a couple of things that, for example, when you look at the Twin Otter, it's quite an old design. You're starting a seaplane now from scratch. We have decided to take this approach, use extract as much performance as possible. So we have done some optimizations, which I would say are innovations in terms of aerodynamics. So the first one was the optimization of the floats. The floats, they are there. Ideally, you don't want them, right? But they need to be there to basically provide the righting moment once the wing or the floats touch the water, to basically bring the wings back to a level condition. So they are basically sized in terms of the volume. So they have a minimum volume that they require to have to provide this righting moment, and you want to minimize drag. So there is a method that targets this sort of optimization that is called an adjoint method. And it's basically a method that, given a certain restriction, targets to minimize or optimize for a certain quantity. And we use this method to minimize drag. So you can see what's happening with the drag as you iterate. And the resulting differences, they're quite small. So it's the sort of thing that is basically not accessible unless you do a very quantitative study like this one. And with this sort of method, we've been able to save or to find some drag counts which are super important for the range of electric planes. And the other thing that I think would be interesting to mention was the design of the flaps that we performed. So we also used an optimization technique there. It's called the genetic algorithm optimization. And it based on landing requirements, selected the type of flap, did some initial estimations based on some empirical data, and then optimized using this method for the arm, and then checked in 3D and in the wind tunnel. So I think it was quite a complete study that we did. And it was also good because we managed to do a very quantitative trade-off study between a Fowler flap that is more complex, but has, of course, better performance, and a plain flap which is much simpler in terms of the mechanism and so on, but of course has a lower performance. I'm not going to go into the details of these curves, but basically what we saw was that, of course, the Fowler flap, given that it is optimized for each position, it cannot outperform the plain flap, but the difference was not enough to basically justify it for the added complexity of that mechanism. And in the end, basically we could basically confirm this in the wind tunnel, and we decided to move with the plain flap, given this quantitative study that was made. And it was also interesting because when you look at the literature, if we selected the deflections only based on literature and statistics, maybe we would go to a deflection that was too much. So the literature indicated something like 35 degrees for this type of case. But what we to some massive detachment of the flap. So it was not performing well, and it was not leading to the lift coefficients that we required. And in the end, we were also able to confirm that in the wind tunnel. So I think it was a good study, and it was a good way to basically extract as much performance as possible. And by doing this sort of method, we now have a quite short takeoff and landing performance for this airplane, which is a differential characteristic of the design.
I can also add that it's critical that we lower the landing speed because of the sea states as well. We want to go into waves and things like that. It's very, very difficult to do that if you retain a high speed. So we try to lower the speed as much as we can. That's why we put so much effort into these methodologies as well.
Brilliant, thanks. Well, just in terms of the electric propulsion side of it, is there the obvious benefit is lower carbon, but does it also enable you to do things that maybe were difficult on the conventional aircraft, and like what are the challenges as well?
Yeah, I mean, you mean if you get some benefit because it's electric, you mean?
Yeah.
Things. Well, they're very effective, the electric motors. So of course, we get a good torque and good power out of them, and the power is immediate. So there are some benefits to it. Now, on the flip side of that, I would say that the weight benefit is not really that big. I was expecting more in the beginning, I guess, but it's very similar to a PT6 installation when you gather all the bits and pieces you need together in an nacelle. So they're not that huge benefits there. But of course, controlling that motor, you have the ability to pinpoint how you want to ramp the motor, how you want these things to work. So you have so many more things that you can adjust and optimize around. So that's very good regarding the electric side, I would say. And then we also have the option to have redundant systems, so multitudes of inverters feeding multiple engines on the same shaft as well, so you can kind of get redundancy out of your units as well.
And
so that's also
that's okay. Thanks for that. Because redundancy is very important in aerospace as well. We've got to have things fail, and it still flies. So that's good. With the high starting torque, does that help you sort of like get up out of the water maybe more quickly and it do that initial accelerate on takeoff versus like a turboprop?
Yeah, that detail in.
Yeah, I don't look at it to this level of detail.
But this is kind of the stuff that we'll probably get into on the prototype.
No worries. Okay, so it's to be found out in testing.
I would say, yeah.
Cool. Do you want to talk a bit more about testing, or
yeah, sure.
have you got to the end of there?
Sure. Yeah, well, I thought maybe we could mention a couple of things about the wind tunnel and maybe the numerics and the scale testing. I think that's maybe some interesting topics. Yes, so we did perform a wind tunnel in KTH in Sweden. These are some pictures of our test there. Yeah, people always asking and why we, I mean, nowadays, is it still necessary to do wind tunnel, and why do people, depending on the physical characteristic that you're looking at, and in the end, it's basically a de-risking tool. The physical testing, etc., can really mitigate, I would say, technical difficulties and capture things that in the end would only capture during flight test. And wind tunnel it ends up being quite efficient, I would say, even when you compare it to CFD, because I mean, to get good results from CFD, you also need to spend very long time evaluating the mesh and doing very comprehensive numerics. And in the wind tunnel, once you have a model, you can test a wide variety of things pretty quickly. In CFD, each alpha is basically a polar, and it requires a lot of computational effort. And also in our case, being the startup, being the first plane that we develop, I would say the tool calibration is also pretty important. I would say it's really important to basically have different sources of data so we can compare and see if things are being are being consistent, right, between the numerics, the semi-empirical, and the wind tunnel. So this is something that for a company that has never developed a plane before, I would say it's pretty important. And looking at these numbers, looking at these tests, it gives confidence on the results, and gives I would say it increases a lot the chances of success, and basically de-risks a lot the program. So this is the sort of stuff that we test. We developed this model in-house with our designers, and it was made in a way that it was very modular. So we could basically, all of these things that you see here in different colors, they can be removed and replaced. So we could do things from changing control surfaces to removing completely an empennage, or to removing a nacelle, or to removing a wingtip. So there was this modular breakdown that was very interesting to basically be able to see how the different things were contributing to the final result. And so we did that. We did control surfaces, which is basically used also for modeling, also for the simulator. We did different types of visualizations, like the ones you see here. So with UV light, with smoke. So this is also very, very interesting to see. And yeah, this is just some example of the stuff that you can see, right? By doing this sort of analysis, you can really pinpoint which characteristics need to be optimized. So for example, here we basically concluded that the nacelles were degrading the maximum lift more than we were expecting. So it was in the end something that we had identified as an opportunity for improvement. And coming to the challenges, it's a very small wind tunnel. So the cross section is of 2 times 2 meters. So if for those who are thinking about aerodynamics, they're already thinking about the Reynolds number, right? So we have a Reynolds number that is basically 10 times smaller in the wind tunnel. And this basically leads to difficulties, leads to mismatches. So mismatches such as these that you see here between what our prediction was in the numerics and what ended up being measured in the CFD for the lift coefficient. And we did our best to try to understand that. We also saw some differences in the way the plane was, the flow topology was behaving close to stall. So, for example, in the wind tunnel, we saw the flow stalling very clearly towards the inboard of the wing, whereas in the CFD it was happening more simultaneously. So, in that sense, the CFD prediction was leading to a more optimized behavior, let's say. So in order to try to study that, we did some dedicated numerics. So we tried to model the wind tunnel with the walls and the sting and the corresponding Reynolds number. So I think this was a very, very detailed study that people not so often do. And we could capture some of the differences, as you can see here, for example, in the pitching moment curve. We see here also that there is a tendency because of these, we don't really know exactly what is causing what, but the combination of everything seems to be leading to a degradation of the lift coefficient. And interestingly enough, we also saw that the combination of these 3 things is basically causing the flow to behave similarly to what we saw in the wind tunnel. So if you during this simulation of the sting plus the walls and the lower Reynolds number, we saw that the simulation was able to do this sort of, I mean, the gaps and everything, they're so small, right? If you look at the gap of the flag, for example, it's a few millimeters, and any uncertainty on the manufacturing, any smoothness issue or anything like that, if you take it to the airplane scale, is going to be pretty large. So it ends up leading to some to some basically robustness issues of the testing.
Yeah, and as aerospace engineer, it is actually like this sort of thing's very exciting because it really isn't very often that you get to design an aircraft from scratch. Most of the big companies that work on aircraft put out quite similar iterations. So, yeah, no, it's really cool to see, you actually doing these tests, like understanding it for the first time, building the models, iterating, all that kind of thing. Um, Awesome. So just thinking about like how the aircraft when it's eventually designed, how it will be used. Could you talk us through like who you think will be the initial early adopters of this and how that might change as you scale? So like would it be replacing ferry routes, island hopping, coast to coast journeys like you showed earlier?
It's kind of the nice thing about I would say the seaplane sector, because it's already an established industry.
Yeah.
So what we see as an early adoption strategy would be a replacement strategy, basically. So we're already talking to, well, you see this nice model here. It has the livery of the Nordic Seaplanes guys down in Copenhagen. So they fly between Aarhus and Copenhagen. That's also a 160-kilometer route. And I think it's a very, very good example where they are already, struggling a little bit with the municipality on having access to the cities because of noise, because of pollution. So they are looking around, a little bit like in desperation of trying to find alternatives to the products they already use. They have, I think, 2 twin otters on floats today. And they have connection to the Maldives operators as well. I think the owner there is partly started that company as well. So the seaplane industry is quite small, and it's quite clear how that replacement strategy could work. So what we are aiming to do is to kind of go into the operations that they do and make sure that we have a product that fits sort of that kind of day-to-day operation. And they typically fly a seasonal operation, so it starts in April, and then they fly until September, and then they move airplanes around to South Europe or do other things in the wintertime, right? So it's a bit of a different operation type. And then they fly 5 times a day, I think, on the highest level when they do the operations there. And we can get into turnaround times, the day-to-day operations, what they have to do. The biggest pain point seems to be maintenance, because seaplanes are, subjected to a lot of saltwater corrosion. So what we have to do, what we can do with the electric systems. And then the second thing is, of course, corrosion-resistant materials, composites, titaniums, ceramics, etc. And we can do that today. The technology is mature. It's there kind of to be used. So I think that a modern seaplane today, although it looks like a seaplane from back in the day in a way, it's going to be a highly technological change to the seaplane as we know it. And it will be more of a marine type vessel in a way that will be better suited to go in the saltwater environment, especially because even during day-to-day operations, you need to wash these things all the time. I mean, they flush engines once a day. There's all these kinds of things that we've gotten into with operators, and it's very valuable to see what they're doing there.
And yeah, just from the maintenance perspective, like one of the benefits of electrification is like an electric motor is so much more simple than a gas turbine with so many moving parts and the big variations in temperature and fatigue and that kind of thing. So I could see that being a lot of people really liking the fact that there's less moving parts. So yeah, just kind of getting towards the end of some of my questions. So I suppose it'd be interesting to know what your view of like the future of air travel in general will be, if you over the coming decades. Yeah, go for it.
Maybe we both get to answer. You can go first, Kenzo.
I believe there is as I heard of these days, there's no silver bullet, right, for this problem, and I think it will come of different things. And in my opinion, the technology that batteries are nowadays and the technology that electric planes basically is now, I would say that they're probably limited to shorter routes and smaller planes, like the one we are developing now. And as you grow bigger, you probably need to maybe go possibly to something a little bit more complicated, like a hybrid technology, and then eventually hydrogen if you go to an even bigger size. And then if you're talking about conventional aircraft, maybe sustainable aviation fuel would be the way to start. So I believe that the solution in terms of sustainable aviation will probably be a combination of all these different things, and they will start with different types and different sizes of aircraft, most probably. Yeah.
Yeah, I kind of a similar view there as well. I think the interesting point with the seaplane, I think we mentioned a few times, is the fact that we have these short routes already there. So it lends itself to electrification, but we're also low flying vehicles where we fly mostly VFR, kind of low. That also helps on the energy usage. And you could also say that if you fly routes over water, then maybe you could even push on reserves. That's a political question, whether or not you can do so. Reserves that look more like helicopter reserves. So you have that going for you as well. And the other thing is that we could also remove the landing gear. Certain operators don't need the landing gears. That would give you another 300 to 400 kilos of payload to you. So I think that right now, the way I see the world in terms of my experience based on battery technology and the possibilities that are there, this is right now the only very clear viable thing that you could do tomorrow, as I see it, right? Because I think over land, I think you need longer range to compete with modes of transport. Right?
Just if you could put yourself on mute. I'm just going to mute a few people. Sorry about that. There we go. I think that should be it. Sorry.
Okay. Yeah, so I think once you go over land and you have your IFR reserves and your challenges on that regard, you're already challenged a lot on getting these ranges done. So I still have a very hard time getting my head around some of the numbers I see out in the business today, to be honest. So I think we're all doing ourselves not really a favor by talking too loudly about 600, 800,000 kilometers and whatever, because at the end of the day, the physics will just slap us all in the face, and nobody will invest in all of this stuff. So I think we have to be honest about like the state of technology, and it is leveraging what's going on in other sectors, right? We can see huge benefits on marine sector development. All the ferries in Norway are electrified, so the port sides are electric. We've got boats that are electric, so the marine technology is already there in a way to be able to accommodate this. And then you've got the automotive industry that are pushing really hard towards new technologies. And we need to be at a state where we can be sort of flexible and adapt these kind of technologies, because I think that's where the investments are really, really huge at the moment. And in aerospace, we're seeing big bankruptcies and big shifts in the where people have already spent so much time, effort, money to develop stuff, and it just ends up in a dead end. So right now, I mean, we're at the back end of a sort of an investment cycle, is my feeling. So right now, I'm a little bit like, I believe that we can raise the necessary funds, but it's not super easy, right? So we have to be honest about the fact that it is a work needs to be done like proper, and we need to, through all the stuff you just saw in terms of what we're doing with the tests and the modeling of the airplane. Now we need to get this thing into the air and show the real full-scale aircraft as soon as possible for our little teams to be sort of progressing in the right way, right?
And just on the political side, I suppose kind of two-part question. When you talk to politicians, do you sort of emphasize the benefit here of, industry-wide developing these technologies in Europe, in Norway, high performance batteries, motors, electrical control systems that will benefit like both the industrial, like kind of clean industrialization of the region, but also like the skills and knowledge that will also be useful in other sectors. Um, and yeah, when you talk to governments, like, are they keen to help, or like, do you think that there's maybe specific policies that could accelerate what we're doing in sustainable aviation?
Yeah, I try to talk about this a lot. We have gotten visitors broadly from big parts of the Norwegian government sector, I would say, in different stages. And we always bring this up, how important it is to, especially in Norway, because we don't have an aviation industry of sorts. We don't produce any planes. We produce parts for planes here and there, militarily and things like that, but we don't have any companies doing this kind of stuff. And that's why we currently, in our small team of 30 people, we have 16 nationalities coming together from everywhere, from Embraer to across the sector, coming to Norway, establishing themselves here, getting families here, really gunning for it in Norway. And I try to say that this is I think this is well spent sort of support when it comes from the government in terms of funding, So we have gotten some funding from the state, and we're trying to get more, right? So we want to show that this has super high value, not just for our company, but bringing these people to Norway and this competency to Norway makes complete sense. So yeah, there is broadly in Norway, there is big acceptance, but it has taken quite a bit of time for people to understand that there is an entity trying to produce planes in Norway. Mm-hmm. I think they thought they would bring electric planes to Norway, but the fact that it's actually being made here, that is something that's taken time for them to understand that it's actually happening,
Yeah. So. I really like the idea as well, because I'm in Scotland, and that there is, if I want to go, I've got some family that live in Oslo, and if I wanted to visit them on a train in a sustainable way, I've got to do a big loop down to London, across to France, through Belgium up. And if I could just go across the North Sea, potentially only not much more than an hour flight, in an electric aircraft from like Aberdeen kind of thing, or Edinburgh, that would be awesome as well in terms of improving regional connectivity. So just final question, so then we can have 10 minutes of Q&A. Have you got any advice for, we're a group of aviation enthusiasts and workers and students. If there are students or workers listening to this that would love to get into the world of electric aviation, electric seaplanes, what advice would you give to them?
Should we do an answer each?
Yeah, you have an answer.
I can go.
Yeah, that's do you want to go?
Yeah, sure. I thought about this because I saw a question earlier. But
feel free to stop sharing your slides as well, actually.
Sorry?
If you fancy, you could also stop sharing your slides. Just so people can.
No, what I was thinking about is more about you're touching on one of the most difficult parts of the project, actually. It's getting talent in the company. So people keep asking, like, what is your biggest challenge technically, right? Is it building the wing? Is it building the propulsion system? No, it's actually finding the people with the mindset and the attitude and the competency to be doing something like this. Because when you're a small team doing a clean sheet airplane, you need engineers that have a very flexible sense of their operations. So they get involved with a lot of different things. And I've seen that is big. That is a big challenge to find, because a lot of the industries are let's say the large heavy industries, they have a lot of specialists, and you need specialists for a lot of reasons. But in a small company like ours, I mean, a mechanical engineer can get one day he's working on a wing bracket, the next day he's on a propulsion rig. I've got a fuselage guy doing propulsion rig now, like moving people around, and they need to be sort of adaptable and flexible and having the attitude that this is okay, and things like that. And we have been giving people we're giving people tasks when we review people, so they do a task for us, and that's how we review their engineering processes. And there are many ways that people sort of attack these tasks and do these tasks, but it reveals this big the way that people do their process very clearly. And for me, it's always about, do you have the curiosity and the interest of getting involved with new stuff and being able to pull valuable things out of sort of a new subject that you haven't seen before. So I would say people that want to design airplanes or want to get involved with startup companies, that, if you're only looking at one thing, you might want to get out of your comfort zone a little bit, maybe do, other technical tasks or try different things. Because in these interviews, we will be testing whether or not you can sort of do a value chain of things at the same time, from like doing a sketch on paper to delivering hardware at the end in a way. Now, some areas like flight physics, I would say is super important to have way more speciality, because that's super valuable. But also inside that field, there is a super wide variety of things that you can get involved with, right? So but you're a very small team, right? And all our teams are very small. So
Kenzo, what about you?
Yeah, I mean, some advice for someone who's starting now. I think that, yeah, I would say, as Thomas said, I agree that the curiosity is one of the important things. Yeah, I mean, find something you like and then try to understand as much as possible about that. And I tend to say focus more on the technical part when you are young. And I sometimes see people who are just finishing graduation and they're already looking for some management or some position like that. And of course, that is also very much valuable. But if you have also a good technical background, that will make you a better manager in the future, probably. And also, yeah, I think you need to find something that you kind of enjoy, the everyday tasks and the path there, right? Not thinking about the end result. And yeah, I think that's more generic. But if you're trying to work with aviation, it's usually the goal is so long. I mean, it takes so many years for a plane to fly that if you just focus on that, I mean, you need to find something that you like and that you can basically develop on an everyday basis. And yeah, I would say
Cool.
that's
Great.
that's
Yeah,
it.
no, that's really good advice. So focus on the fundamentals and the
Yes.
technical understanding, but have flexibility and probably it kind of sounds like that sort of startup mentality of being able to turn your hands to different things and understand what other people in other areas of the office are working on and why. Um, yeah. Awesome. And yeah, I think that's a good analogy for, the future of aviation as well. We have to enjoy being part of the journey because we don't quite know what's coming. And it's important that we're, we can evolve our thinking as we go, a little bit like
Mhm.
your aircraft flaps were evolving with the genetic design tool. So cool. Thanks very much for answering my questions. What we can do is we can stop recording, George, if you're